So probably most of my talk will be some half fairy tale of what to think about the data, and maybe in the last 5 minutes I'll tell you something about the Flatiron. So, but most of the discussion to modify the thinking about the Drude model. So let me first thank my collaborators on this project. So it was done in collaboration with Andrei Mishchenko and Naoto Nagaosa from RISC Saitama, Lode Paleh, who is here from LMU, and Abhishek Kumar and Dmitry Maslov from the University of Florida. And the paper was just accepted to PRO. So first I will kind of discuss a conceptual question, maybe the puzzle, and only at the very end I will just discuss the behavior of mobility for Fröhlich polarons in the strong coupling regime. So the phenomenological story will start from the classical equation of motion. And ultimately, at some point, I will just mention one Russian name, probably nobody, okay, except Chris and Felix, nobody have heard of. So the classical equation of motion with friction, when we write it down, we don't even care how strong is the friction. We can add any number for friction we like. So I can simply rewrite the friction term in slightly different kind of notation. So you write down friction as mass divided by tau, and the tau is relaxation time. So just imagine that your equation of motion is given by this equation. It's already written in the frequency domain. And you ask the following conceptual question. Classically, it's perfectly okay, and you immediately say yes. But quantum mechanically, you say, okay, whether it's formally possible to have some dynamics, which looks like this, but the number which you have here, which we call relaxation time, is formally turns out to be much bigger than temperature, and you consider the system, which is thermodynamic linear response, nothing special. So I'm talking about the particle in a translation invariant system. This particle couples to the environment, everything is at temperature T, and you end up with the classical equation. If I do it classically, semi-classically, then the relaxation time is, inverse relaxation time is much bigger than T. So of course h bar is 1. And whether this is possible to have this type of behavior and the limit of temperature goes to 0, and what all of this means quantum mechanically. So classically, no problem whatsoever, but quantum mechanically, actually, you are a little bit in trouble with when you do it.
And Nikolay, we don't have impurity scattering.
No, no impurity. This is important. This is no impurities. This is translation invariances. Because with impurities, it's slightly different story. So that's the first question, whether it's possible in principle to have this type of quantum mechanical behavior, or somehow the quantum mechanical system will figure out the way of always having h bar tau not being much bigger than temperature. And essentially the question goes back to the uncertainty relation, which says, okay, typically to define energy, which is, say, temperature itself, if it's a thermodynamic system, you need long enough time. And if you don't have enough time, kind of your relaxation is much bigger than 1 over T, how you can even define the thermal energy of order T? So whether this kind of condition, which I'm trying to mention here, is not in violation of the uncertainty relation between energy and time. So it appears it is. And the second, okay, well, whether, it's again conceptual question, I'm allowed to ask it without any quantification. Say, okay, can I simply rewrite this equation in such a way that I pull out omega squared in front and simply call the remaining piece as frequency-dependent mass renormalization, which diverges in the limit of omega goes to 0, or if temperature goes to 0, as if mass starts going to infinity. Whether all of this makes sense and whether this alternative reading is actually reasonable. Okay? So the other question, for example, it's now related to the problem which I will discuss at the end. Suppose you study standard electron phonon problem. You have an electron which is embedded in the material and it's scattered by phonons. If I consider, say, optical phonons at some frequency omega, I understand that the number of thermal phonons available for scattering will first increase exponentially fast at low temperatures, but then it will increase as a power law in temperature. But definitely the higher the temperature, the more phonons I have for scattering. But if I measure mobility, suddenly maybe I can have a minimum. This minimum would be very strange because formally I have more and more phonons at higher temperature, but somehow the particle is moving faster as I increase temperature. Whether this is possible and what all of this will mean. And the two questions that I will discuss, they are related. So essentially to develop this type of minimum and have mobility increasing with temperature despite bigger and bigger number of phonons be available for scattering, essentially happens in the limit when the previous condition becomes in trouble, when tau t gets too small. Okay, so those are the questions. So let me now more or less kind of switch to something which is everybody knows classically, so I go back to the classical description. So suppose I just consider something which is the Drude model, when I simplify the complexity of scattering events and simply replace everything with some relaxation time. Of course, relaxation time can be computed using quantum mechanics, using cross sections and the rest. But then you solve the equation for the mobility using very simple model, which is known as Drude model. So you say that momentum relaxation is force minus typical relaxation time, that's momentum change in time, and mobility itself is velocity divided by f. And if I solve it in frequency domain, this gives me a very simple structure for the mobility. And from this mobility, I can try to deduce what is the scattering time. If I look at the static limit, so frequency is 0, formally static mobility doesn't tell me explicitly what is scattering time, what is mass, because I only can look at the ratio. Classically, of course, I don't have a mass normalization when I just do it, but I understand that if the particle is scattered, it has to be coupled to the environment. If the particle is scattered to the environment, you expect some mass normalization to happen. And typically, kind of at the level of the Drude model, you say, okay, quantum mechanics maybe somehow will change effective mass from m to some other value, but otherwise this equation will be valid. Maybe I have to replace m with m star. But unfortunately, the static mobility itself will not measure every quantity separately, only the ratio between the two. But then I can go back to the full frequency dependence and say, okay, just look, if I do the real frequency, a real part of the mobility, it's a Lorentzian line shape. And then the Lorentzian line shape will immediately tell me that half width determines tau. And if I know tau, I can determine what is the particle mass. And that's the typical kind of picture within the Drude model. So this is the Drude peak and the standard understanding, okay, how you interpret different values from the Drude model. Now, when all of this is working, so essentially I have to assume for this model to work and kind of to do the full proper calculation, I have to do the kinetic equation because I have to compute tau properly. But the underlying assumptions are that you have very rare scattering events, rare in the sense that the particle is propagating ballistically on a much longer time scale than the collision itself. So I can very well isolate collisions, which requires that the mean free path is much bigger than the particle wavelengths. So this is the typical condition for the applicability of the kinetic equation. So that's the first condition. I will call it the Monte-Carlo transition criterion, even though it was introduced kind of maybe used also in this slightly different context in disordered systems. This is more or less the same condition for the applicability of the kinetic approach. So I need the mean free path to be long enough relative to the particle wavelengths. And the particle wavelengths itself, in the translation invariant system, thermodynamic limit, everything thermal, it's roughly the de Broglie wavelengths determined by temperature. On the other hand, you can say, okay, well, the other case, which I am also kind of implicitly implying in this kinetic equation, is that I can separate scattering events. And if the particle has typical energy for the temperature, then the kind of the scattering time itself, which okay, how long I have to propagate between the two, it has to be long enough. So which means I have enough time to determine what is the particle energy between the scattering events. So the particle will change its energy, but it happens on a time scale which is much bigger than the energy itself. So this is called the Planckian bound. Well, the two conditions actually are not different from for the translation invariant system, which I discussed, because if I simply take this condition, tau is bigger than 1 over t, multiplied it by the particle velocity, which is square root of t, I'll immediately get the mean free path is much bigger than lambda. So it's not a different condition. So they are consistent. So your Ferrigel criterion or Planckian bound, they're both telling me that, okay, they have to be satisfied to use the kinetic equation. And both imply that, okay, if I divide this by mass, then mobility has to be large in units of 1 over mt. So that's the standard kind of setup. When you can use kinetic equation, you have the Drude peak and the interpretation of the Drude peak. So the question now is, what happens if those conditions are violated? But of course, well, the first question you can ask, whether this is possible in principle. Whether I can have something which is real part of the mobility, looks like a Drude peak with very good Lorentzian line shape, but this Lorentzian line shape is such that the half-width is much, well, half-width which is shown here is much bigger than temperature. Whether this is possible in principle, and after I just look everything, I just see that the mobility is much, much smaller than 1 over mt, whether this is possible in principle.
So, Nikolay, I just have a question. In general, so we are in translation invariant system. Yep. Tau is inelastic scattering. Right?
Yeah, this is supposed to be an elastic transport scattering.
So if it depends on temperature, it also depends on omega.
Of course.
Right. So it's actually not really right that the curve has this shape, because tau depends on omega.
So you are saying that this is not possible to see experimentally?
No, I'm saying that actually in experiments, if you look carefully, and if you look for the effect, you will see in this curve non-Drude form, which is due to the omega dependence of tau.
Perfect. So your answer is this cannot be seen experimentally. I'm saying you will see this experimentally.
Most of the time when it's seen, it's because scattering rate is dominated by elastic processes.
Okay.
If you really put the elastic processes to very low, you can pick up the omega dependent terms in
Antoine, perfect. This is perfect.
I love your answer.
Perfect in the following sense. Here is the question, whether you can see this curve experimentally, so it's perfect Lorentzian line shape. The half width is much, much bigger than temperature, and the mobility is much, much smaller than 1 over mt. Whether this is possible experimentally. Yes, I understand everything. The real physical scattering time has to be such and such. Maybe it has to satisfy the Planckian bound. But what I see on this curve is says, okay, the half width is much bigger than 1 over t. Then I say, okay, maybe my interpretation of the data is totally wrong. So the half width, maybe it has nothing to do with 1 over tau. And maybe the entire frequency dependence comes not from the tau depending on frequency, but something else. But the real part of mobility looks like a Lorentzian light shape, looks like a Drude peak. Everything looks like conventional picture, but the half width is much bigger than the temperature itself. Whether this is possible in principle. So my answer is this is possible in principle, but the entire interpretation of how you look at the data is totally different. So the half width has nothing to do with the scattering time. So this will be the end of the story. So formally you have an answer which can be interpreted like conventional Drude, but it will violate everything. It will violate the Planckian bound, it will violate the mobility values, but the interpretation will be different. Now, what is the experimental system which has this type of property? So I'm just claiming that the mobility of the next experimental system is exactly like this, with half widths much bigger than temperature, but it's very nice Lorentzian light. So what's the experimental system? So the system itself is the electron bubble in helium-3. So I have an electron, but if I inject an electron in helium, it will create a vacuum space of very large radius. So this is my bare particle. So the bare particle has very large radius. It has effective mass roughly 200 helium-3 masses. And the other kind of thing which is specific for the bubble is that it has very large scattering cross-section. So if I measure cross-section in units of the Fermi momentum in helium-3, this dimensionless parameter happens to be 25. Okay? Even despite 3 pi squared, it's not enough kind of to make it small. So it's still 25. So those are the parameters which are characterizing this bubble. So it has transport scattering cross-section which is large and it has large effective mass. That's how you start. Then you start measuring mobility. And you see that, okay, when you go to temperatures much smaller than Fermi energy in helium-3, you start approaching to lower and lower temperature. Ultimately, the experiment was done all the way to a millikelvin when you go superfluid. So the mobility stays constant. So that's an experimental. This is kind of very early experimental data of 68, but ultimately this was done all the way to TC. The mobility stays constant as temperature gets smaller, smaller, and smaller. But now we are in trouble, according to the previous discussion. So if I just look at the mobility, that's the value. The value of the plateau, which is temperature independent itself, I can easily explain. Because at very high temperature, the particle energy is much bigger than the recoil. So if I just look at the recoil energy, P Fermi squared divided by m, that's the recoil energy which I can get from the Fermi liquid, it's much smaller than temperature here. So I write down the Fokker-Planck equation, the problem solves exactly. So I can compute the value of the plateau. So the transport scattering time is given by g, P Fermi squared divided by m, so g is 25. So the plateau itself can be explained. But then people say, okay, yeah, this is true as long as the recoil energy can be neglected. But as long as I go to temperatures much smaller than the recoil energy, I have now just to do the proper scattering theory, and the mobility has to diverge as 1 over t squared. So this would be, the dash curve would be the standard thinking. The moment I have to care about the recoil, the mobility should start shooting up. Because now I have to care about energy momentum conservation on the Fermi surface, and the particle mobility goes as 1 over t squared. But experimentally it doesn't. Notice only it doesn't care about T0, nothing happens at T0. It just keeps going, keeps going, keeps going, until I hit TC and nothing happens to this constant. It stays constant. Okay, so what's observed is constant. But this constant is a problem with the Planckian bound, because if I just use this constant and the bare effective mass, so this is my tau, This tau, if I write it down in terms of recoil energy, is G0, T0. So before I actually reach the point where recoil is important, I already strongly violated Planckian bound. So tau minus 1 computed from high temperature limit gets much bigger than T0, the evident temperature, well before I reach the recoil energy. And then when I go to recoil energy, just nothing happens. I just keep going with the same kind of line, as if recoil is never important, no matter the temperature is much smaller than P Fermi squared divided by m. So that's how the experimental system behaves. It just totally ignores the recoil effect. Okay, but I'm definitely already in trouble with the Planckian bound somewhere here, but I can go 100 times lower in temperature. Second, well, okay, well.
I have a question.
Yep.
What is the compressibility doing?
Compressibility of what?
Constant.
Helium-3? Nothing, it's Fermi liquid regime, very deep, nice Fermi liquid. Nothing special.
So the whole range
So
of
the
Fermi energy is somewhere here.
3K. I mean, Fermi energy is 3K in this
Yeah,
system.
well, maybe even less with effective mass normalization.
No.
So this is 100 millikelvin, 10 millikelvin, all the way to superfluid.
You're thinking of the impurity, you're not thinking of helium-3, you're not doing the treatment.
Yeah,
of
that's what I
helium-3.
was asking, yeah.
So he wants to know the corresponding quantity to the compressibility of these
Of these objects.
objects that you're treating.
Or it's almost incompressible. So it's a very hard sphere because the potential which is creating the bubble is very hard.
We
It's,
know that.
It's electron well.
No, but it's very dilute, no?
Yeah.
Or are you
No, it's just one electron. It's one bubble. So
It's
I'm
a
not
single
exactly
polar.
sure what the
It's
question is.
single
polar.
It's single particle in Fermi liquid. Yeah, it's not many bubbles. It's just one bubble. No, I was thinking that you're asking about the compressibility of the bubble itself.
No, no, compressibility of the
Yeah, no, it's just one
He
particle.
wants to use Einstein's relation.
Yeah, that's what I want.
Yeah. Essentially, yes, you say diffusion goes to 0. So diffusion constant goes in a linear fashion goes to 0. As if diffusion will be 0 at 0 temperature. And this continues all the way to TC, but then you change the nature. It's not Fermi liquid anymore, it's a gas state. Well, furthermore, I can prove that for G much larger than 1, this type of behavior, constant, will continue down to exponentially low temperature if it was not going superfluid. If it was not superfluid, but still same Fermi liquid, it would go to exponentially low temperature. It's E minus 25, so essentially assume that to temperatures which are picokelvin, you will keep going with the same constant. Nothing will change. Moreover, you can prove that the mobility dependence on frequency is the perfect Lorentzian line shape for the real part. So that's the exact, more or less, with good control parameter, this is the correct answer for the frequency dependence of the mobility. So everything looks like Drude with enormous violation of the Planckian bound and everything. So that's the experimental system. So classically, this is, again, I repeat, is no problem, but quantum mechanically makes very little sense, because how comes that I can define particle energy as temperature when the scattering time is much, much bigger? Scattering rate is much, much bigger. But then there is one model which was also kind of doable exactly, and that's even better than helium. This was done by a Russian radio engineer in 1959. Feynman just invented path integrals, and Magalinsky asked the question, what would be the quantum model reproducing the classical equation of motion with friction? What do? You take a particle, you couple this particle to a set of harmonic oscillators with linear coupling, you adjust the spectral function to what now is known as the ohmic case, and that's what Magalinsky did, and it was called quantum Brownian motion. This is an exact copy of later what was done by Feynman Vernon, and ultimately reclaimed again by Caldera and Leggett. So, but first it was done in 1959, and that's exactly what you want, the quantum interpretation of classical equation of motion of friction, how it will look like. Well, of course, if you integrate bosonic degrees of freedom exactly, you end up with the action which is quadratic for this particular case. If you couple linearly to R, that's the effective action in Matsubara frequency, and it looks like classical equation of motion, but in Matsubara domain. Now it's quadratic function of R, so you can compute all answers exactly because all integrals are Gaussian. Okay, so that's the standard ohmic dissipative model. And because it's so simple, essentially any answer you get from this ohmic dissipative model is exact. And that's where you end up with the mobility, which is purely Lorentzian line shape for the real part. So that's the solution of the ohmic dissipative case, and that's exactly how bubbles in helium-3 behave. So you can derive it now rigorously from Fermi liquid theory that that's exactly what the bubble will do. They simply fit in the ohmic dissipative kind of environment picture. You can have this type of behavior with as large tau as a formal parameter, because here I'm not claiming that tau is a scattering rate. In no way. I'm just saying, okay, well, tau is just a parameter related to the Hamiltonian. In the Hamiltonian, you have coupling constants, you have some spectral density of different frequencies for the bosons, and if you compute this spectral function, you simply characterize it as linear function of omega m divided by tau, and that's the definition of tau. So it's essentially characterizing how strongly you couple to the bosonic degrees of freedom, but I'm not claiming that this is a scattering time yet. It just appears in the equation as if it's a relaxation time in the right place, but I'm not claiming that it is. So that's where I come to the alternative interpretation. I say, okay, well, this is my alternative reading, which I believe is correct. So I will read this action as I will pull out omega m squared, and I claim that the remaining piece here, m1 plus 1 over tau omega m, can be considered as mass renormalization. Of course, in the overdamped regime, this is nothing but words. You call it damping, fine. You call it mass renormalization, fine, because it's the same kind of formula. But now, whether this reading actually makes sense. And my claim is it makes perfect sense for the following reason. Why do I not care about recoil when I reach temperature T0? So you start with, if I say that this is effective mass renormalization, it really tells me, okay, if I substitute here what is tau, it says that effective mass is BMS, coupling constant 25, T0 divided by T, and as temperature goes to 0, effective mass diverges. Okay, so that's the statement. So the effective mass goes to infinity as temperature goes to 0. But now you immediately see that, okay, well, if this is true, the effective mass diverges like this, I never reach the recoil scale. Because if I simply compute recoil energy using renormalized mass, which is divergent with temperature, the recoil energy is always temperature divided by G, but G is 25. So I never reach the recoil energy, which is big enough compared to the particle energy, which is temperature itself. Now how I reconcile it with the physical scattering time, I say, okay, I will insist that the physical scattering time is always bound by the Planckian bound. So the scattering time has to be 1 over T. But then the two pictures simply are compatible with each other because I'm saying that mobility is physical scattering time, which is 1 over T, divided by physical effective mass, which is divergent as 1 over T, but the ratio is temperature independent. It's the same as tau over m. So essentially this ratio is lying to us how to interpret tau and how to interpret m. You instead have to have tau star, which behaves as inverse temperature, and effective mass, which is divergent as inverse temperature, despite having the pure Drude formula. So in the pure Drude formula, half-width has nothing to do with relaxation time. Relaxation time is 1 over T. But in this formula, it's just some constant. Okay? So this is a different interpretation. Just literally saying that you look at the Drude peak, but it's lying you in all possible ways what are the physical parameters of the system. Now, how do I know that this interpretation, it looks kind of bizarre? Why would I interpret kind of this term as mass renormalization? But how do I know this interpretation is right? You go to a superfluid state. The moment you go to a superfluid state, you open a gap. Now the number of quasi-particles drops exponentially fast. You recover the Boltzmann kinetic equation. And in this Boltzmann kinetic equation, you can compute an effective mass. So if I compute an effective mass of bubbles in helium-3b, this can be done, you discover that it's roughly BMS times this coupling constant G, T0 divided by the gap in the superfluid state. And that's literally replacing temperature with the gap in the superfluid state, and the effective mass of bubbles in superfluid helium-3b is renormalized by enormous factor relative to the 200 helium-3 masses. So the effective mass of ions in the superfluid phase can be at 0 pressure. I forgot already which curve is what. One of them is higher pressure, the other one is 0 pressure. So at 0 pressure, this can be, I forgot already why I have two curves. But okay, at least what it says, okay, it's 20,000 helium-3 masses if I do bubbles. Probably dash curve is something else. So that's 20,000 helium-3 masses, that's the effective mass of bubbles in the superfluid phase. So essentially behind the violation of the Planckian bound, there is enormous mass renormalization, and I would insist that in this type of problems, the Planckian bound on the scattering time has to be imposed, but from the imposed Planckian bound, if you violate it formally, you have to claim the divergent mass renormalization. At least in this example, everything can be done more or less rigorously. You can compute effective mass at low temperature in the gap state, and that's how it works. So now I would like to go to polarons, because this is more or less well understood example, but now we go to polarons. This will be a particle coupled to the environment And in semiconducting structures, more or less, well, I have to specify what is the dispersion relation for the particle, what is the coupling constant, and then compute all the other properties. For the Fröhlich model, okay, well, this is just standard cartoon. What we mean by polarons, you just inject an electron, but it will push atoms around, and if I want to move, essentially I have to move with the latest deformation. That's what creates an effective quasi-particle. Now, for the Fröhlich model, what's important is that an electron branch will intersect the optical node at very low momenta, so you don't care where is the Brillouin zone boundary, because all the integrals and interesting effects will happen at low momenta, and then you essentially can use the parabolic dispersion relation for the electrons, because that's just the beginning of the electronic spectrum in the semiconductor. You can use constant dispersion relation for the optical phonons, because that's the important part where everything happens. And the coupling constant is given by the Coulomb interaction differentiated, because it's coupling to the displacement of the Coulomb field. So that's the standard Fröhlich polaron model with all the coupling constants specified. And it's kind of very strange number of different 2, square root 2, and pi for only one reason. To define the dimensionless coupling alpha, because if I compute lowest order correction to the polaron energy, it's given by alpha times omega. So that's just to simplify the final answers. So essentially alpha is the dimensionless parameter which is characterizing strong coupling versus weak coupling. So that's a standard Fröhlich polaron model. Well, you can compute mobility in the Fröhlich polaron model in 2 different limits. One limit is very low temperature when the number of phonons is exponentially small. So this is essentially a perturbative case when you can do kinetic equation. And this was done by Langras and Kadanov. Even though right now people argue that this formula is still not correct, even after, what, almost 50 years. There is still some literature claiming that the prefactor to this formula is different. From 3 half temperature to 5 half temperature to a constant number like in this formula. So, but whatever we kind of were able to analyze, looks like Langras and Kadanov were right. So that's the expression, but anyway, it says, okay, it's exponentially large mobility, and within the same calculation, you can replace mass with effective mass, but since the calculation is based on the perturbation theory, this is only valid for alpha much less than 1. This is the effective mass corrected perturbatively. You can also compute the mobility for, sorry, this is much bigger than omega. So for very high temperatures, so this is wrong sign, you can also compute everything because now you have Migdal theorem. The particle energy is much bigger than phonon frequency, and all vertex corrections are small in the adiabatic parameter. So then the calculation can be done essentially rigorously for any value of alpha, and the mobility goes down as square root of temperature. So I'm not showing details, but this is doable. Now the problem happens in the strong coupling regime. So essentially the 2 formulas can be matched more or less nicely for small values of alpha, but if alpha is much bigger than 1, we know that perturbation theory will fail. Well, you know it from just doing ground state calculations, which we did a long time ago by Diagrammatic Monte Carlo. That's essentially how everything started. You see that the effective mass, first it just increases, but when alpha, the coupling constant is large, say 5, 6, the effective mass normalization is already large. It's roughly an order of magnitude up. Effective mass is already, this is log 10, so this is roughly 10 for alpha equals 6. But at the same time, the z factor for the polaron just drops to almost unobservable value after alpha equals 6. So it just drops to almost 0. So we're definitely outside of perturbation theory when we go to large values of alpha.
But is the claim that there is a transition or the
No, there is no transition. This is just z factor just goes to 0, and here it just gets exponentially small.
Because in the product of the particle, there were papers where Albert Schmidt made a claim that there was actually a sharp transition. When the particle
No, for the
mobilized.
Fröhlich polaron there is no sharp transition. It's analytical all over the place. I think there was a German paper claiming that this is a theorem, that for this type of problems for polarons, you're not allowed to have sharp transition. You can only have it in models which not sign positive. If the model is not sign positive, like in the case when you couple to the hopping terms, say in 1D, then you can have some sharp features. But if you have everything positive, they are just either convergent series, and then essentially from the analytic behavior of convergent series in the coupling constant, you can claim that transitions are not possible. So that's what happens if I try to plot the data for large alpha into limits which I can roughly understand. So you go to low temperatures, it's exponentially large. I also use effective mass, which was computed for low, very low temperatures. So that's very well controlled, maybe up to a factor of 3.5, but still it's exponential. And then you plot high temperature limits, and they more or less kind of create some mismatch. If I just naively continue the 2, they just separate by a large value. But then anyway, the moment you plot what will be the your Rieger criterion or the mobility bound to say that everything is beyond quasi-particles, everything below the dashed line is beyond quasi-particles. So essentially something for mobility happens in this region, but it's not part of the kinetic equation. So how do we solve it? This is done again by diagrammatic Monte Carlo because everything is sign positive. We can compute current or velocity correlation function for the polaron. It's simply just same diagram as we had before for the polaron, but now on the beta circle. And it's very easy estimator for the current correlation function because everything is done in momentum imaginary time representation. But in momentum representation, the operator for the velocity is just particle momentum divided by mass. So you immediately compute from the Monte Carlo simulation of all diagrams on the circle with any number of phonon lines to any arbitrary order, everything is sign positive. You immediately collect statistics for the current correlation function. So that's the Monte Carlo estimator. So for whatever parameter you have on this graph, you estimate Km, which is the Fourier component on Matsubara frequencies of the momentum contribution to the this is Ki, but momentum is a function of time, but it's piecewise because I have finite number of insertions, and that's why kind of taking the Fourier transform is trivial because I can easily integrate the exponential function. So and then just the current correlation function is given by this expression. This can be done very efficiently. So essentially in the calculations we go to statistical error bars for the Matsubara space with accuracy of better than 6 significant digits. Looks like it's good enough because we know Matsubara signal with accuracy of almost 6 significant digits. But unfortunately, the kernel for analytic continuation to get the static mobility is ugly. So 6 significant digits for the Matsubara space is not enough to get mobility with accuracy of, say, 10%. You are much worse. If mobility is large, even this is not enough to give you an answer with accuracy of a factor of 2 or 3. But if it's overdamped, it comes back because if the spectral density is broad and there are no sharp features, the analytic continuation works much, much better. So in the overdamped regime, actually the technique works much better than in the regime where there is kinetic equation. So essentially when the kinetic equation applies, you can get your Matsubara signal with any accuracy you like, you will never ever get the correct answer for the mobility. That's when the kinetic equation works. When the kinetic equation fails, this will start working with reasonable accuracy. Just because the frequency signal gets much, much broader. So, and that's the data. This is coming from 6 to 7 significant digits in the Matsubara space. So if coupling constant is 2.5, we're entering the strong coupling regime. You suddenly see that, okay, well, there's some behavior at high frequencies, but then the exponential increase is kind of almost delayed, as if I know this slow dependence, which is square root of time, is somewhat delayed, and then it takes off. But of course, here our error bars, when the kinetic equation works, they just explode. It's not reasonable. But then if we go to alpha equals 6, the data show that I start developing a maximum. So essentially, I have some dependence at high temperature, and we feed the correct data. Maybe our error bars are exaggerated, but we are trying to be very conservative in terms of what we do, just to be sure. Of course, as I said, okay, it's almost impossible to get correctly the exponential increase. But you definitely start getting somewhat better in the overdamped regime, and you develop a maximum. So no matter what we do, just it's consistently saying, okay, well, you develop a minimum and then a maximum and the mobility. And in the region where you strongly violate the Planckian bound. So at this point, I'll just go to my previous interpretation and say, I have to insist that the Planckian bound has to be satisfied for the physical scattering time. And if it's satisfied for this physical scattering time, essentially any discrepancy here, I have to attribute to the effective mass normalization. But then it immediately tells me how to interpret the data. It says, okay, well, at very low temperature, I have heavy mass. Say effective mass is increased by a factor of 10 for alpha equals 6. And with this heavy effective mass, I'm entering into the region when my temperature is roughly over the order of phonons, and now the particle starts moving faster than the phonons can follow. The particle should start undressing. So during some interval in temperature, I have to undress the particle and to go from effective mass 10 to effective mass 1. That's what I have for the high temperature regime. That's where the vertex corrections are small, Migdal theorem works. So here it's light particle scattered by phonons, but here I enter with particle with effective mass 10. So essentially the maximum is explained, yes, you increase the number of phonons, but undressing the effective mass by a factor of 10 is a more important factor. So the particle gets lighter, and that's why the mobility goes up, because it's a lighter object. So despite larger number of phonons in the system, the mobility goes up because they are getting lighter. So it's effective mass renormalization undressing. So that's our interpretation how you can get the mobility minimum for polarons in this system. So essentially, I'm essentially done, but probably from the previous discussion we already understood that, okay, interpreting the data, even if it's perfect Drude, it's totally lying you about what is the physical scattering time. In this case, it's not even Drude. Here I just totally agree with Antoine, even though it's possible to have Drude with violation of the Planckian bound and frequency-dependent mass and scattering time. In this case, it's totally different. Not only you don't have Drude, so you have Drude at low temperatures when the kinetic equation works, but the moment I enter the strongly coupled regime, when everything is formally overdamped, I see that instead of Drude, I have anti-Drude. So there is no any signature of the Drude peak. Yes, I have some constant mobility in the region where it's getting up, but the frequency-dependent signal has nothing to do with the Drude peak. It's just totally different, not interpreted. You cannot interpret this in terms of this any scattering time. It's just totally different signal. Probably I'll just stop at this point. So essentially the message I am having in my mind that if you have a particle strongly coupled to the environment, whenever the Planckian bound on the inelastic scattering time, which you compute formally, the moment it's violated, you have to start thinking that, okay, probably you are also facing the problem of enormous mass renormalization at low temperatures. So essentially there will be some regime where frequency-dependent mass, frequency-dependent scattering time, all of this is very important, and it's impossible to interpret the data naively from the Drude peak. But the effective mass renormalization is more or less hiding in the bushes when you look at the data. That's why the data can behave in a totally counterintuitive way. They can develop minima and maxima because you have both. You have the number of excitations, but it's maybe competing with the effective mass renormalization, creating some non-monotonous behavior of the mobility. So, and that's my conclusion.